So in the part 3 of this series short course, we are very happy to have Matlab Code to come and to give us a series of lectures. Perhaps you have known already that Matlab has some special experience that everyone has. I think after I'm a graduate from Minnesota, and he went to the DE shop.
Lawrence Livermore
Lawrence Livermore first, okay. So he went to the Lawrence Livermore National Lab, 这个国家实验室，待了一阵子。And then everyone moved to DE Shaw. If you go to the website, DE Shaw is very, I think probably the biggest company working on the molecular dynamics. 化学的那个分子动力那个，在纽约一个非常大的一个公司 DE Shaw 很特别哈。So he also has experience in industry, and then Emma moved to Georgia Tech. So again, Georgia Tech has probably one of the biggest computational science college. So that's really some very big, important academia institute around the world. So you see, Emma has a different experience in industry, national lab, and academia. And he is definitely the expert in this high-performance computing. And of course, maybe you know that Emma won the Golden Bear Prize. Yeah, so it's 就是那个 Golden Bear 就是它是这个高效能计算最大的一个奖。So I think this is just one example to show Emma's expertise. So anyway, I think this is a very good opportunity to learn this very advanced and interesting topics from an expert. So I will just give the time to Emma. So let's please join me to welcome Professor Chong.
Thank you. Thanks very much. Thank you very much for the introduction. It is my great pleasure to be here to give you guys a series of lectures on this topic that is of great interest to myself, and I'm very happy to try to give you some of my knowledge and try to get some of you interested in this topic area. If I can just say one sentence about what this part of the what this short course will be about. This is that one sentence. Fundamental techniques of parallel computing and high performance computing apply to sparse linear solvers. Okay, so there are a lot of very advanced techniques, but I want to focus on just the fundamental techniques. And from the fundamental techniques, I think that you can start to understand and appreciate some of the more advanced techniques. There's really no time in this course to talk about all of the new solvers, all of the new techniques that are available today. So maybe that will be yet another course. And applied to parallel computing, so what is parallel computing? This is when you have computers that have multiple processors, multiple nodes, SIMD processing, GPUs. It could mean a lot of different types of things where you have multiple compute units that must be used at the same time in order to perform one calculation. Okay, so this is a reality today. There's no more sequential computing. A lot of people will still write papers on mathematical methods that really only work well in a sequential environment, but those types of papers always depress me because they're just not really applicable. You know, they're interesting on their own, but they're not really applicable to real life. So we'll look at these parallel computing aspects in a fundamental way. And also high performance computing, which is an umbrella over parallel computing. So parallel computing is an aspect of high performance computing. A high performance computing includes more things than just parallel computing, because if you want to have computer programs operate efficiently, you have to also take into account reducing the amount of memory movement and other aspects that are much more than just parallel computing. Okay, so this is why I don't want to say just parallel computing, but also high performance computing. And then the topic of solvers is quite large, but we're going to focus on sparse linear solvers. This is my expertise. I think this is also really what the first part of the course concentrated on. But the techniques that you will learn will be applicable to much more than sparse linear solvers. They will be applicable to other things as well. But for the purposes of the next 12 lectures, we'll focus on sparse linear solvers. Okay, so how will this course operate? We will have a number of assignments and a project to help you learn the material. In other words, there will just not be some lectures. There will also be some things to help reinforce what you learn in the lectures. So let me talk about that a little bit. So we'll have some exercises. We'll have some assignments. And we'll also have a project. Okay, so at the end of each lecture, I will give you a short exercise to do for the next class. Okay, the short exercise is only meant to take about 1 hour of your time that evening or the next morning. And it should be fairly simple. And what you should do is you should write up your results very briefly and then hand it in at the beginning of next class. And what we will do is we will collect these exercises, and they will not be graded, but they will be graded for participation, meaning if you don't hand in something, then you don't get credit. Okay, so credit will be given for participation. Okay, so this is after each lecture and due at the beginning of the next lecture. And then we will also have assignments. There will be 3 assignments. Okay, 1 at the end of each week. Okay, and I will post these assignments on a website. And they will generally be due on Fridays. Okay, and this is a more involved exercise, just like an assignment that you might receive from any other course. Okay, so 3 weekly assignments. And you'll have 1 week to do them. So there won't be one due this coming Friday. Probably we will have the assignment posted this coming Friday, and it will be due the following Friday. So, so 4 weeks from now, your last assignment will be due. And then there will be a project. And this is a much more involved exercise as well, requiring some more of your own creativity and initiative. And I don't know when it will be due. I guess you guys will set the due date for that. But it will be due. So the projects you will probably start after the lectures are over, and you will have some time to finish the projects. Okay, so start after all the lectures. And I will, in many of the classes, give you some ideas for what good ideas for projects are, and also at some point I will write up some ideas for projects that you can look at. Okay. So luckily, I will not be the one giving the grades. I'm only here for the lectures, so someone else very mean will give the grades. But to give you an idea, I think, of how much work you should put into each one of these components, I'm going to suggest something. Okay, so I'm going to suggest the exercises are like 25%, assignments 35%, and project 40%. Okay, so you can't just skip one of these things. You have to do everything in order to get a reasonable grade from whoever is going to be grading. All right? All right, so because we have exercises, you probably want to meet with me if you have questions. Okay, so because we have exercises and assignments, so I will hold some office hours. And I'd like to propose Monday and Thursday, 2 to 3 p.m., and also by appointment. So if you cannot make these times, you can just send me an email, and we'll just set up a time. I'll generally be here all day, Monday to Friday. Probably afternoons are better for meetings because I'll be making up a lecture in the morning. And the office hours will be held in my office in this building in room 463. And if you want to contact me with any questions, which I can answer by email as well, by the way. So I can answer questions by email, or you can send me an email to set an appointment. So my email address okay. There's also a website that I'm going to try to maintain in order to pass along information to you, like MATLAB M files. So by the way, I will be using MATLAB fairly extensively in this course. It's not really a parallel computing language, but a lot of the concepts can be illustrated in MATLAB, and it will also help solidify ideas about the algorithms that we'll learn in the course. So I believe most of you are fairly familiar with MATLAB. If you're not, then this is the best opportunity to try to learn more about MATLAB. And the website that I will use, which you can go to right now, is this one. I want to say that we might change the website because this accesses a computer back in the US, and I tried to access it. The access seems a little bit slow, so we may change something to a local machine later on, and if we do, we'll let you know. Okay? All right. So you'll notice that my style is to write on the board. My feeling, especially in more mathematical courses, is that if you write things down at least once, then it will help you learn, as opposed to me showing you a lot of slides. And if you prefer, you might want to bring a notebook and a pen, and that might be a little bit easier for writing down math than typesetting on a machine. Okay, any questions before we start? And if there are questions, you can always ask later. So what I want to do is I want to begin with talking about finite difference methods for numerically solving partial differential equations, just very briefly. And you may already know a lot about this, but as I understand, it was not something that you covered earlier in this course. And the reason why I want to talk about this topic is because there is a very close connection between the types of methods you want to use and the problems that you want to solve. Okay, so we have to say a little bit about what are some characteristics of the problems that we want to solve. And also something that is very important for parallel computing is to understand something about the relationship of the variables in the equations. So this is talking about the finite difference mesh, or in general, some kind of finite element mesh. Okay, so we want to understand the relationship between these meshes and these matrices. And for this reason, I want to just make things very clear and concrete by talking about the finite difference discretization. Okay, so numerically solve. And I'm going to choose a convection diffusion equation. And it's a boundary value problem. Okay, so instead of starting with just a diffusion equation, because some of you may have seen a lot of these before, I'm just going to start with a slightly harder problem, okay, a convection diffusion equation. And this convection diffusion equation that I'll write down is one that has been used a lot in studying iterative methods. So it has a parameter in it, you'll see, the convection parameter. And by adjusting the parameter, you can make the problems have slightly different character. Okay, so the unknown variable will be u. So di squared u by di x squared. So this is the diffusion part, and then we'll have a scalar parameter beta. And the convection is going to, this is a 2D problem, by the way. And the convection is going to depend on the x, y coordinates of the problem. Okay? Okay, so the unknown, whoops, I need some U's here. So the unknown is U, and U could represent temperature or energy density. It could represent the concentration of some quantity, the concentration of a pollutant. Okay, and for instance, we could use such an equation to understand what is the steady state temperature distribution in some room, for instance, in some two-dimensional room. So it's a boundary value problem, so we're going to have to define the boundary. So on a region which is just the square from 0 to 1 and 0 to 1 on the x and y axes. And the boundary values, I'm going to say, for this case, very simple. U is equal to 0 on the boundary of the square. Okay, so this is setting the value of U, otherwise known as a Dirichlet boundary condition. Okay, and G is some forcing function. Could be some sources of energy or sources of some pollutant, whatever. And this is also given, but I'm not specifying what it is. But this is also a given quantity. And given this equation, we want to find U. Okay. So in general, depending on the shape of the domain, we may or may not be able to find an analytical solution. For this problem, an analytical solution could be readily available. But if we cannot find an analytical solution in general, we want to solve the problem numerically. And the idea of solving the problem numerically is to try to find the solutions at a discrete number of points, a discrete set of points in the domain. So here, let's say this is the x direction from 0 to 1, and this is the y direction. I'm going to do it a little bit weird, y going down. Okay, and I'm going to choose a domain. So we have a value of 0 for the variable u along the boundary, and I'm going to choose a discretization. And that's not the one I wanted to choose. I want to choose a 4x4 mesh of unknowns. Okay. So there are unknowns at each one of these grid points. Okay, and there are also unknowns over here, but they're known values and they're set to 0. Okay, so we want to find the value of u at each one of these grid points. And to do this, we're going to use a finite difference approximation. So we assume an equal spacing. Okay, so we're going to say that we have a m by m mesh, and here m is equal to 4. We have a mesh spacing h, and that is 1 over 5. And each one of these points will have an ij coordinate. Okay, and this is the index of the grid point. The very first one over here will be 1, 1. Okay, and I'm going to use as notation xi is equal to the x coordinate of index I, so that's equal to IH, and yj is going to be JH. Okay, so I'll use these for convenience. And then the finite difference approximation for each one of these terms so let's first consider di squared u by di x squared. Okay. So the approximation here so suppose we want to find it at some ij point. Okay. So instead of writing equals, I'm going to change this to is approximately equal to minus ui plus 1 comma j plus 2 ui comma j minus ui minus 1 comma j over h squared. Okay, so you may have seen this from other courses. I'm not going to go into how this arises or error term, things like that. Okay, and so this is just one of the terms here. Okay, so we got something similar for the y term. For the convection term, I think it's a little bit more interesting. Okay, so there we'll just resort to calculus. So from calculus, di e xy times u over di x approximately equal to, and we'll just use the definition of a derivative. Okay, so that's e x plus h, so h is the mesh spacing, presumed to be small, times y, u evaluated at x plus h comma y, okay, minus e x minus h times y, and u evaluated at x minus h comma y. And this is a first derivative, so this is all over 2h. Okay. And if I write one line down, are you going to be able to see? No. The cameraman says no, so the camera gets gets veto power. So I will write the next line over here. So what we can do is we can write this in terms of the variables at each one of the grid points, okay, as e x I plus j, x plus I plus 1, right? So this is using this notation back here, times u I plus 1 comma j minus, I need a y as well, right? So yj e x I minus 1 times yj u I minus 1 j, and this is all over 2h. Okay? So these two are the terms in the x direction, and there are similar terms in the y direction. And what I want to draw your attention to now is that I've written a Matlab code that generates this matrix, and it's posted on this website, and I'd like you to take a look at it. Okay? And the name of the file is matconvdiff.m. Okay? And this function takes two parameters. One is m, the mesh dimension, and the other is beta. Okay? So if we have beta equals 0, then we have a pure diffusion problem. And we have beta larger, we can have some kind of convection approximated. And you'll notice that I've only used central differences for the convection term. And if you know about upwind differencing, that is something that could be important to use if you in cases where there is large convection. And on the first assignment, I'm already imagining that we'll use slightly different discretization, and you can compare what the effect of slightly different discretizations is on different problems. Okay? I mean on different methods. All right, so any questions so far? Okay, so this is the discretization in this equation of the left-hand side. We can also discretize the right-hand side. So for the right-hand side, let's say we have Fij, which is some value of the right-hand side at the ijth grid point. And this is just equal to G evaluated at xi comma yj. Okay. All right, so let me go down to this board again. All right, so now we have m squared variables, okay, and we have m squared equations, one at each one of the grid points. All right, to solve for the m squared variables, we have, because it's a linear problem, m squared linear equations. And this can be written down in matrix form. Okay, so this can be written down in the form matrix A, right, times a vector U consisting of all of the unknowns at all of the grid points equals F, which is this F over here, all of the right-hand sides at all of the grid points. And because I chose 0 for the boundary values, this simplifies the problem a little bit in terms of assembling what these equations look like. Okay, so this is a set of m squared variables in m squared equations. Okay, so if you haven't seen this before, this is motivation for why solving linear equations like this is important, because many numerical problems, such as this one coming from numerical PDEs, leads to solving such equations. Okay. All right, so something important for this course is to understand what is the structure of this matrix A. Okay. So I'm not going to be so concerned about the values of the matrix A right now. The values, you can figure out from the discretization. But I'm going to write down for this problem, this 4x4 mesh, what the matrix looks like. And I'm going to draw it like this. So A has this structure. And I can write the equations in any order and the variables in any order. So I have to, if I'm going to write down a matrix, I have to specify the ordering of the grid points. Okay, so let me go back to this and say something about the order of the grid points. I don't know if I can bring that down with. All right. So now I will now use the pointer. All right. So you can write this in your notes. The ordering of the grid points we're going to use is this one. So 1, 2, 3, 4, 5, 6, etc. So this is called the natural ordering. Okay? So if we write down, if we look at what is the pattern of the matrix here, if we only look at the first 4 equations by themselves, we have this pattern where the x's represent possible non-zero values, and if I haven't drawn an x, that means we have just a 0. Okay, so this is the pattern, a tridiagonal matrix, the pattern of a one-dimensional discretization, finite difference discretization with just 4 variables. And we have 4 of these lines, right? So we have 4 of these blocks. So we have 4 of these blocks. Might not be so clear, but you know what the pattern is. Okay, so these are all of the connections in the x direction. Okay, and then we have connections in the y direction, and they look like this. Right? So there's also connections to the y direction over here, but this goes off of the grid, connecting to the boundary values, and the boundary values are 0, so we can just ignore them. Okay? Okay. So I took some time to draw this. This is a very common structure. You're going to see it over and over in this course. Okay? So this is what the structure of the matrix A looks like. Now, not all problems have such regular structure. I want to point out that if we were interested in computing, let's say, the temperature distribution of this chair or stresses on this chair, it's not just a regular square object, right? So we can't use a regular finite difference type of mesh. And what is typically used is a mesh that is irregular. Okay? And if you have a mesh that is irregular, you cannot use finite difference formulas. Okay? But there are, in general, other methods such as finite element and finite volume methods that could be used. And they will lead to matrix structures that are more complicated. But in any case, we always have matrix structures where the unknowns are coupled to nearby unknowns, because this is what is used in approximating the derivatives that show up in the differential equations. Okay, so the structures, a very important point is that the sparsity structures that come from real problems are not arbitrary. You might look at it and it looks like, oh, it's all random all over the place, but there's a lot of structure here that is available and generally should be exploited for parallel computing or other forms of efficient computing. Okay, so there are some numerical properties of this as well, such as positive definiteness and things like that. We'll go into those as we need to. Okay. Any questions so far? Okay. So we want to solve this set of equations ax equals to b. There are a number of ways of doing that. We are going to talk a lot about iterative methods for doing that. But before we do that, I want to say something about direct methods for solving these equations ax equals to b. And the reason why I want to talk about direct methods in this course is because a lot of the preconditioners that we may want to use later on could be related to these direct or LU or Cholesky factorizations of this matrix. So in order to understand some of these preconditioners later on, we want to understand something about direct methods. Also, what is important to understand about direct methods that you'll see in a moment is that the order of the grid points, in other which is related to the ordering of the equations and the ordering of the variables in the matrix, is very important in Gaussian elimination because it determines how much storage and computation will be needed. And ordering is a very important concept in parallel computing. Ordering and partitioning, how you divide up a problem, is very important in parallel computing. So what I will talk about, what I want to try to motivate now using direct methods is this important concept of ordering. Okay, so we're going to solution by Gaussian elimination which is a direct method. Okay, and as review, or in case you haven't seen this before, we have the matrix A. We're going to factor it into the product of a lower triangular matrix and an upper triangular matrix. Okay, so I'm going to assume that there's no pivoting to make things simple. And we want to solve AU equals F. Okay, and if we have the factors LU, I have a capital U and a lowercase u. L capital U lowercase u equals F. So I've substituted the factorization. And the solution can be found by solving with the triangular factors. Okay, so this is via forward and back substitution. Okay. So the reason why we factored it is because we know how to solve with a triangular factor very easily. Via is just substitution. And in particular, it would be incorrect and unnecessarily expensive to try to compute the inverse of L and then multiply. So this is what I'm writing here is explicit, well, should imply triangular solves. Okay, so this is the solution by Gaussian elimination. And to compute the L and the U, we take the matrix here, and this is what I'm sure you all know. We try to create zeros in the lower triangular part of the matrix. Okay? And so let's do that. It's a lot easier to do when we don't have to have values because we won't make any arithmetic errors. But we can do this on the structure of the matrix and see what is the structure of the L and the U that arises. Okay, so let me use a different color. So it's easiest if we try to do this in some order. What I'm going to do is I'm going to introduce zeros in L column by column. Okay, so first I'm going to eliminate this non-zero in the lower triangular part. Okay, and to eliminate this, I multiply some factor of the first row, right? And I add it to the second row. And if I do this, you'll notice that this non-zero is going to create a non-zero in that location. Okay, and this non-zero is called fill-in. Okay, it means that the sparsity pattern of L is going to have more non-zeros than the sparsity pattern of the lower triangular part of A. Now let's look at what happens when we try to create a zero over here by multiplying some appropriate, by adding some appropriate multiple of the first row. And you'll notice that this non-zero now creates a fill-in in this location. Okay? And we can go through the same process with this, with the next column, creating non-zeros here, etc. And you'll notice that fill-in will occur in all of these locations. Okay, so it's actually a fairly good exercise to try to do this by hand. Fill-in, and in fact, fill-in will occur within these outer bands of the matrix. So let's write that down.